All right, so in this video, we'll just look at some conceptual questions about friction to help you to increase your understanding of how friction works. All right, before we look at some more problems involving friction, let's look at some conceptual questions to see how you're coming along with your understanding of friction. In this situation, we have a box sitting stationary on a floor with a constant horizontal force, F1, is applied to the right. We also have a vertical force, F2, pushing down. Now we're going to increase F2 from 0, and we want to see if the following will increase, decrease, or remain the same. So there'll be several questions. So the first of all, as we increase F2 pushing down from 0, does the magnitude of the static friction change? The static friction remains the same. Remember, the static friction is balancing the force F1 to the right, preventing the box from sliding. We're given that the box is stationary on the floor with the constant force F1 to the right. So the static friction to the left is also constant and exactly equal in magnitude to the force F1 to the right. So that is not going to change. So as we increase the force F2 downward from 0, will the normal force increase, decrease, or remain the same? The normal force, of course, will increase. So as we push down harder and harder on the box, the table is going to push up equally as hard as F2. So the normal force will increase. Now, what happens to the maximum value of the static friction as we push down harder and harder with the force F2? Will that increase, decrease, or remain the same? That, of course, increases. Since the maximum value that the static friction can be depends on the normal force, so as the normal force increases, the maximum value of the static friction will also increase. But the static friction force itself will not increase. That will always be exactly equal and opposite to the force F1. So as we push harder and harder downward with the force F2, will the box slide eventually? No, of course, the box will not slide. The only way we can get the box to slide is we have to increase F1, but we're given that that one is constant. So if we don't change F1 to the right, the static friction doesn't change, and the box will remain stationary. The only way we can get the box to move without increasing F1 would be to reduce the normal force so that the normal force times the coefficient of static friction is less than the force F1. Since we're not doing that in this problem, the box will not slide. All right, here's another situation. Here we have a box on an incline. So a box has a mass M. It's held stationary on a ramp by the frictional force on it from the ramp. So I just put this box on the ramp and it doesn't slide because the friction is holding it in place. Now I'm going to apply a force F up the ramp, and I'm going to gradually increase that force from 0. So without the force F, the box does not slide down the hill. It stays still. Now I'm going to apply a force upward and gradually increase that from 0. So during that increase on the force F, what will happen to the magnitude and direction of the frictional force on the block? All right, so initially, before I start pulling up the hill, I just have the box at rest on the hill. I have the component of the weight down the hill, mg sine theta. So if it's not moving, the static friction up the hill will be exactly equal to mg sine theta. And so the forces sum to 0. Now, as I start to pull up the hill, and the box is not moving, well, now my static friction is going to be less than mg sine theta. So the net force up the hill, me pulling, plus the static friction will equal mg sine theta down the hill. So the static friction is going to decrease the harder I pull up the hill. Now eventually, when my pull up the hill equals the weight down the hill, so in other words, when my force up the hill equals mg sine theta, at that point the static friction becomes 0. So the static friction during this process will go from mg sine theta down to 0. All right, so now what happens if I pull harder than the weight component down the hill? So in other words, if my pulling force up the hill is greater than mg sine theta, now the box will want to slide up the hill. So to prevent that, now my static friction will point downhill, so that the component of the weight down the hill, mg sine theta, plus the static friction will equal to the force that I pull up the hill. And so as I pull harder and harder, the static frictional force down the hill will get greater and greater. So that if the box is not moving, the mg sine theta down the hill plus the static friction down the hill will always equal my force up the hill. Now, if I pull harder than mg sine theta plus the maximum static friction, at that point, static friction is not enough to hold it, and the box will slide, and I will have kinetic friction. All right, so to review the whole process. So initially, before I start pulling, static friction is pointing up the hill to prevent the box from sliding down the hill. Now, as I start to pull up the hill, I need less and less friction to hold the box, and so the static friction component up the hill will decrease and get smaller and smaller, eventually reaching 0 when my pull up the hill equals the weight down the hill. Now, if I pull harder up the hill than mg sine theta, static friction force now reverses and points down the hill to prevent the box from sliding uphill from my pull. And it will continue to increase until it reaches the maximum value. Now, if I pull up the hill greater than mg sine theta plus the maximum static friction, the box breaks free and slides, and we have kinetic friction. Here's another conceptual question. I have a box sitting at rest on a ramp that's inclined at 35 degrees, but the box is on the verge of sliding down the ramp. Since it's on the verge of sliding down the ramp, that means the static friction is at its maximum value. Now I've replaced the box with one of the same material, but it has twice the mass and twice the area of contact with the ramp. So at what angle will this box be on the verge of sliding? It will be on the verge of sliding at the same angle of 35 degrees. Remember that the friction does not depend on the area of contact. So this one will also be on the verge of sliding. It doesn't matter that it's twice the mass and twice the area of contact. What matters is the nature of the surfaces in contact with each other. Since they're both the same materials, the coefficients of frictions will be the same, and so this will also be on the verge of sliding. All right, so let's break down the forces involved in a box that's on the verge of sliding down the hill. So here in the diagram, I've drawn in the forces. We have the weight down, which of course will be equal to the mass times g. And we have the normal force of the ramp pointing upward, perpendicular to the plane of the ramp. And then we have the maximum static friction pointing up the hill. So I break the weight component into a component parallel to the plane and perpendicular to the plane. The one parallel to the plane, of course, is mg sine theta, as we have seen before, and the one perpendicular to the plane is mg cosine theta. So we have that the normal force will be equal to mg cosine theta, since we're not moving in that direction. And the maximum static friction, of course, is mu sub s times the normal force. So since the box is on the verge of sliding, that means the maximum static friction up the hill will equal the weight component down the hill, which is mg sine theta, and We place the normal force with mg cosine theta. We have the maximum static friction is equal to the coefficient of static friction, mu sub s, times mg cosine theta. So I set mu mg cosine theta equal to mg sine theta, and notice the mg divides out, and we get mu cosine theta equals sine theta, or mu equals tangent theta. So this is a way we can measure the coefficient of static friction. We put the object on the surface that we want to measure the coefficient of static friction, and we incline it until it just starts to slide and measure that angle. The tangent of that angle then is equal to the coefficient of static friction between the two materials. All right, so you should be able to answer this question now. A packing crate is placed on a 20-degree incline. If the coefficient of static friction is 0.65, will the crate slide? So keep in mind what we just did in the previous example. You should be able to answer this. So did you get no? No is the answer. Why is that? Well, if I take the tangent of 20 degrees, I get 0.364. So that means our coefficient of friction was given as 0.65, which is greater than 0.364, so we will have enough friction to prevent it from sliding. If our coefficient of friction was less than 0.364, then it would slide. But since our coefficient of friction is greater than 0.364, then it will not slide. So the point where it's going to slide, the coefficient of friction will equal to the tangent of the angle. So if our coefficient of friction is greater than the tangent of the angle, we'll have enough friction to prevent it from sliding. All right, so that's the end of this video. And in the next video, we'll look at some numerical examples in different situations involving friction. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel, and please subscribe. I hope you find my videos useful.